In this video, we are going to talk about reactions of organic molecules. Specifically, we are going to touch on several types of reactions, including combustion reaction, substitution reaction, addition reaction, oxidation reaction, condensation reaction, and hydrolysis. Equipped with knowledge of different types of reactions organic molecules can go through, we can then discuss reaction pathway, which comprises of how to produce certain desired chemical from what we have currently. And then we are going to talk about some concepts related to reaction pathway, such as yield of reaction. So this is really important in industrial applications. So the first type of reaction that we should already be very familiar with, since we have already talked about this extensively in the first few videos of this playlist, is the combustion reaction. So it occurs with fuels. And since we are talking about organic chemistry, so we only focus on organic fuels, those that contains carbon and hydrogens. So alkane, and alcohol. So those are the three types of organic molecules that can undergo combustion. So something to note is that carboxylic acid does not combust. Alkanes is not a fuel, because we know that the bond strength of the carbon to carbon triple bond is very low, so it is too reactive and hard to get in pure form. So that's why it is not a fuel. So all those molecules, whether it's alkane, alkene, or alcohol, they burn using oxygen gas to form carbon dioxide and water. So this is complete combustion. Of course, for incomplete combustion, you can get carbon monoxide or even carbon as your product. So combustion is redox reaction. It involves a transfer of electron, or gaining of oxygen and losing of hydrogen. So some of the general things you need to know: fuels are always oxidized, and oxygen is always reduced. I should say oxygen gas. And all the combustion reactions are highly exothermic. So it produces a lot of energy when they combust. And it is precisely the purpose of fuel, which is to provide energy. You should also know how to write balanced equation for combustion. If you don't, please refer to my previous videos. So the second type of reaction is substitution reaction. So this substitution means you are replacing atoms, usually hydrogen atoms, with some other atoms. Based on this description, you should know that by some other atoms, usually we mean things like chlorine, bromine, etc. And so we can form haloalkanes. So the formal definition is an atom or functional group is replaced by another atom or group of atoms. So this is most common in alkanes. So those with carbon-to-carbon single bond. So we know that alkanes, they are saturated hydrocarbons. So because it's saturated, we know that the single bond is very strong. So the carbon-to-carbon bond is very stable and does not really want to undergo lots of different types of reactions. So substitution reaction is one of the few chemical reaction it can do. So that's why usually for substitution reaction, we have focuses on alkanes. So anything with entirely carbon-to-carbon single bond. And because we know that carbon-to-carbon single bond is stable, then if we want alkane to undergo substitution reaction, it is not spontaneous and require UV light as catalyst. So I think the function of UV light is to provide some extra energy so the CC single bond can be disrupted. And once the bond has been disrupted, it can form covalent bond with other species, such as chlorine atoms. So this reaction would not occur spontaneously or automatically. We require a catalyst for this reaction to occur. And usually, we replace hydrogens in alkanes by one of the group 17 atoms, so the halogens. So let's have a look of one example. So the reaction between methane and chlorine gas in the presence of UV light. So this is really important. If in the exam they didn't say that UV light is present, then you should answer that this reaction will not occur. So nothing will happen. Only if we have a catalyst, we can get this reaction. So methane is a gas at room temperature. Chlorine gas is also a gas. And you write this arrow to indicate this is the forward reaction. And above the arrow, you write UV light. So this indicates that you are using a catalyst. And essentially what happens is the chlorine, one of the chlorine atoms replaces the hydrogen atoms. You can't like swap them over. So now you have CH3Cl plus HCl. So this is what is going on. So you would have CH3Cl, which is also a gas, plus HCl, which is also a gas. So this is the reaction between them. Notice that HCl is a gas, and not aqueous solution, because we do not require water in this chemical reaction. So this is only one possibility. Of course, we can go further. So we already have this chloromethane, but we can substitute the hydrogens further with chlorine. So we can do reactions once again to get dichloromethane. And then from that, we can do the reaction again to get trichloromethane. And we can continue going until all hydrogens have been substituted by chlorine. So in the end, we get tetrachloromethane. And the chemical equation looks something like this. So you have CH3Cl gas combined with chlorine gas. With UV catalyst, you get CH2Cl2 plus HCl. And then you continue going with this. You use dichloromethane and mix it with chlorine gas to get trichloromethane and HCl. Then starting from trichloromethane, you combine again with chlorine gas. On the UV light, you get tetrachloromethane. So this is really the end of the reaction you can do. You cannot go any further. So another question that you might ask is it possible to control which hydrogen or how many hydrogen is substituted? The answer is no. So all of this is a purely random process. So it is really purely random. So why is it random? Because the covalent bond between carbon and hydrogen are the same strength. So which CH bond break is really just random. So a problem naturally arises. So when we are producing haloalkanes, then we can produce a lot of different products. So we can produce chloroethane, dichloroethane, trichloro or tetrachloroethane. So how do we separate them out into different fractions? So we can actually get pure substances. So maybe we just want tetrachloromethane. So how is this possible? Just like crude oil, which is a mixture of different lengths of alkanes, it must be separated by fractional distillation. Because we know that those chemical substances have different molecular mass and therefore different melting and boiling point, we can use fractional distillation, which is hot at the bottom and cold at the top, to separate out different fractions. So you would expect the CCl4, which is the heaviest of the four, have the highest melting point and boiling point. So you should collect CCl4 from the bottom fraction. And conversely, the chloromethane should have the lowest boiling point. So you should collect it at the top. And that's how you separate out the different product formed by substitution reactions using fractional distillation. And we can do something even further. Haloalkanes can also undergo substitution. So for example, the chloromethane. We know that the chlorine atom is more electronegative than the carbon atom. So the bond is polar. The covalent bond between C and Cl is polar. And because it's polar, then something like an overall negatively charged hydroxide ion can replace the chlorine with a hydroxyl group. And this creates alcohol. So where does the hydroxide ion come from? It usually comes from a strong base. Like sodium hydroxide or potassium hydroxide. So with this information, we can write this type of reaction as an organic pathway. So this is the reaction pathway. So you are going from haloalkanes to alcohol, with R represents the rest of carbon chain. And Cl is the chloral functional group, and OH is the hydroxyl functional group. And one of the characteristics of this reaction pathway equation is that it only shows organic molecule as the reactant and product. We know that the hydroxide ion, the OH minus ion, is participated in this reaction. So it actually displaced the chlorine atom, and so to transform haloalkanes into alcohol. But it is not part of the reactant or product, because for reaction pathway, we are only focuses on the organic molecule. And note, unlike the chemical reaction formula, like this one, the whole OH ion actually participated in the reaction, so it is not a catalyst. So you should be very careful when reading between those two types of formulas, or reaction formulas. For the reaction pathway, the thing at the top is actually also one of the reactant. And for this proper chemical equation, the thing at the top indicates catalyst. So don't be confused between these two topics. So although we know that this process produces alcohol, but we should also be very careful where the chlorine atom is. So for example, if your chlorine atom is here, and then you react this with hydroxide ion, then what you will get is a secondary alcohol. And if your chlorine atom is at the end, and then you swap it with the hydroxide ion, then you are getting a primary alcohol. So we really need to be very careful of where your chlorine is located, because secondary alcohol and primary alcohol, they undergo different types of reaction and will produce drastically different types of product. So this process of replacing haloalkanes with hydroxide ion to produce alcohol, this is spontaneous. And we do not require any catalyst, which is really nice, because if you have catalyst, it adds cost and it adds complications as well. So another way you can substitute haloalkanes is to undergo substitution reaction with water. But this process happens very slowly, and thus we require a catalyst to do this type of reaction. So the process looks like this. So you have a haloalkane and then you have water. You add a catalyst. Which is usually some type of acid. It produces alcohol. And one of the leftover hydrogens from the water and the chlorine atom will produce HCl. And this is in aqueous form, because we know that water is present in this system. So this is another substitution reaction that we can do with haloalkanes. And the end product is the same as the previous example, where we react haloalkanes with hydroxide ion, which is the product is also alcohol. So another substitution reaction is the substitution to form substitution of haloalkanes to form amine. So the general equation looks like this. So you have haloalkane with NH3 ammonia as one of the reactant to form amines. So this is really the organic compound of the reaction. And the inorganic ammonia is at the top of the arrow. And it is also part of the reactant. So in general, the reaction looks like this. React with NH3. And the chlorine atom will be displaced by NH2. And again, we have HCl as the remaining product. So the H comes from one of the hydrogen atoms left over on the ammonia. The chlorine atom is the one that has been replaced out or substituted out from the haloalkanes. Another type of reaction is called addition reaction. So this only occurs in alkanes with CC double bond. So the reason why it is called addition, so if you recall addition from mathematics, 1 plus 1 is equal to 2. So you have two reactant molecules and forming into one product. So this is essentially what addition reaction does. And during this process, the CC double bond will be converted into CC single bond. And you will see how this would happen later. You go from something that is unsaturated to something that is saturated. And one of the most important advantages of addition reaction is that we know exactly which molecule will be formed. So recall from the substitution reaction we discussed earlier, we don't really know which molecule would be formed. So that's why we need fractional distillation to separate them out into different fractions so we can get pure molecule. But for this one, for the addition reaction, we know exactly what will be produced. So the first addition reaction we are going to look at is the addition of hydrogen gas. And this requires a nickel catalyst with about 500 degrees of temperature. So really high temperature. So it's a very simple reaction. And then you add, so this is ethane, and you add hydrogen gas. So what happens is literally the double bond break, and then you add the hydrogen atoms across. So this is literally what would happen. So the end product is ethane. So that's why it's called addition. So you have one molecule, another molecule here, but the product is only one. So you are kind of adding those two things together. Another example is the addition of halogen gas, such as chlorine, bromine. So this occurs without catalyst. So still you have the ethene, and then you add, for example, chlorine gas. And what you do is you break the double bond, and so each carbon can now connect with one more atoms on both sides. So this is the final product. So as you can see, because you are breaking the double bond, and after you broke the bond, then each carbon can have one extra atoms be connected to it. So when you are undergoing the addition reaction, it is only possible for the chlorine atom to be added on both sides of the molecule. But if you are undergoing a substitution reaction with ethane, then because, as we have discussed, all the CH bonds are the same strength, it is very possible that the chlorine would appear on one side of the molecule. So you really don't know which product you are forming. But with the addition reaction, it is always added on both sides of the molecule, since the breakage of double bond affects both carbon atoms simultaneously. So in this case, you really know that you will be only forming 1,2-dichloroethene. So this is one of the key advantages of addition reaction. You can also add things like HBl, HBr, hydrogen chloride, things like that. So this also do not require a catalyst. So what happens is you break the double bond, and then the H and Cl will be added on the opposite side. So you get chloroethane. So this is the key advantage of addition reaction. You really have a lot of control over the substance you want to produce. If you want to produce dichloroethane, then you add hydrogen gas, then you add like something like chlorine gas. If you only want to produce chloroethane, then you add HCl. Whereas for this substitution reaction, again, you really don't know what you will be producing. You can also add H2O, you can also add water, but this requires a catalyst of H3PO4. So this is also an acid, and at high temperature of around 300 degrees. So the reaction looks like this. Still have ethane. You add H2O with catalyst H3PO4. And also you need to specify the temperature required, which is 300 degrees. And it becomes, so this H and this OH is from water molecule, and you form ethanol. And there's no other chemical species produced since it is addition reaction. Only one product will be produced. So let's look at several more interesting examples which shows the usefulness of addition reaction. So here, let's look at what molecule it is. There are 4 carbons on the carbon chain, and the double bond is connected to the first carbon. So it is but 1 ENE. So this is the molecule. And let's add this with HCl. And we know that the product would be, we add H on one side and we add Cl on another side because it is addition reaction. So when we look at the product, it becomes 1-chlorobutane. Also, another possibility is that the chlorine atom gets added to the right hand side. And the hydrogen atom added on the left hand side. So here we get 2-chlorobutane. So there is a 50% chance to obtain 1-chlorobutane and another 50% chance of obtaining 2-chlorobutane when we had but 1 ENE as our reactant. But suppose we have this molecule. We now have cis but 2 ENE. And again, we want to add with HCl. So what will be the product? So what will happen is we add the chlorine atom and hydrogen atom on opposite side, just as we have done before. And here you would notice that no matter which side you add the chlorine atom or the hydrogen atom, they are all just 2-chlorobutane. Because whatever arrangement you have, the chlorine atom is always connected to the second carbon. So when you have a molecule like the cis but 2 ENE, for a molecule like this, you are 100% guaranteed to obtain 2-chlorobutane. So this is really a key advantage of addition reaction. If you choose your reactant correctly, there is no uncertainty. So if you only want 2-chlorobutane, you should start with the cis but 2 ENE. Of course, the trans arrangement also works well for this kind of reaction. You still get 2-chlorobutane in the end. So for the addition of H2O, we commonly call this the hydration reaction because we are adding water, so we are hydrating this molecule. So in fact, ethanols are commercially produced via this hydration reaction. Because for other ways of producing alcohol, we would produce some byproduct such as HCl. And we need to separate HCl out from ethanol, which is again complicated and costly process. But for this hydration reaction, the only product produced is ethanol. So there's no separation required. And that's why we prefer this kind of reaction when making ethanol. And it is also very easy to separate out the catalyst in the system. So that's why this is preferred over the substitution reaction. Another useful case of addition reaction is the production of polymers. So essentially what happens is the carbon-to-carbon double bond gets broken. So we form a new bond between the two carbon atoms, the two adjacent carbon atoms. And similarly for this double bond, it forms another link with the adjacent carbon atoms. So this can go on forever with a catalyst to break those bonds. And ultimately you get something like this, which goes on forever. Sometimes with 20,000 individual monomers. So this is called monomers in a polymer chain. So usually we represent polymers like this. The number n represents how many of the monomers is in this long chain of polymers. And we see that this link extends out of the bracket, indicating we have other carbon atoms that are connected to this. The squared bracket is put around the segment of the polymer that represents the original monomer. So from this, we know that the monomer is just ethene, because there are two carbon atoms within this bracket. So that's how we read this kind of diagram. The next type is oxidation reaction. So we have looked at combustion reaction as oxidation reaction. But if we have alcohol, it can also be oxidized by strong inorganic oxidizing agents. So in this case, it is no longer the water that is the oxidizing agent. So when we are doing this kind of reaction, we can produce three things. So we can produce aldehyde, ketone, and carboxylic acid. Depending on which type of alcohol we have and which type of oxidizing agent we have. So usually the oxidizing agent is the potassium dichromate or potassium permanganate. So you are required to know those two oxidizing agents for the exam. So I suggest you to memorize those two oxidizing agents. And the potassium ion is the spectator ion. So what really undergoes reduction is the negative ions that is involved in the actual redox reaction. And it is being reduced. So this is one of the conditions. The another condition is we require acidic conditions. So this ensures we have the H+ ion available. So we can balance the half equation using the Kohl-Hess rule. So I have already covered this Kohl-Hess rule in the redox reaction video. So first, let's look at oxidation of primary alcohol. So this is really a two-step process. So the first step is we go from alcohol to aldehyde. So we have a primary alcohol. So this we have the H plus and the Cr2O7 2- as the catalyst. And this will then produce aldehyde. So essentially we are losing 2 hydrogens. And losing 2 hydrogens means we are undergoing oxidation. So this is oxidation. And step 2 is we go from aldehyde to carboxylic acid. So we have COH, again with the same catalyst, this time with heat, to produce COOH. So we are gaining an extra oxygen, which again follows the definition of oxidation. So this process I have shown you is called the organic pathway. So there's no inorganic product present in both reactant and product. And this is just the definition of organic pathway. So in many cases, we just go directly from the alcohol to the carboxylic acid, because the aldehyde is really just an intermediary step that the process must go through in order to produce carboxylic acid. So because aldehyde is just the intermediary process, in order to produce aldehyde, it is a little bit tricky. So if we want to form aldehyde, we need really gentle condition. So this means we want low temperature and a short reaction time. If the reaction time is very long and then we have a high temperature, then alcohol will be converted all to carboxylic acid, and we do not have any aldehyde available. So this is really help to prevent further oxidation. So we need to remove the aldehyde frequently to prevent it oxidize into carboxylic acid. Because the final product of oxidation, even under gentle condition, will still be carboxylic acid. So let's try to write down the oxidation half equation for propan 1O into propanoic acid. So let's have a go. So this is just a revision of Kohl's rule. Remember, for this oxidation to occur, we need to have the catalyst H plus ion and Cr2O7 2+ ion. So let's have a look. So the first step is to determine the chemical formula of propan 1O. And I recommend you to just draw it out. So we have 3 carbon. 1, 2, 3, 4, 5, 6, 7, 8. 8 hydrogen and 1 oxygen. For the propanoic acid, we have 3 carbon, 6 hydrogen, and 2 oxygen. So we are going from C3H8O to C3H6O2. So the oxygen is not balanced. So for the co-Hess, we first balance the key element. So here the key element is carbon, and carbon is also balanced. So key element is just anything except oxygen and hydrogen. Then we move on to oxygen. On the left-hand side, we have one oxygen. And on the right-hand side, we have two oxygen. So we add H2O to balance the oxygen. Then we look at the hydrogen. So on the left-hand side, we have 10 hydrogen. Right-hand side, we have 6. So we add 4 hydrogens by using the acid in the solution. So we have H plus as the acid. Then the next step is to balance the electrons. So here, this part is neutral. So we need to add 4 electrons on the right-hand side to make it balanced. And the next step is to add state. So here, because we are conducting everything under aqueous solutions, we have water as a liquid. The propanol, the alcohol, is aqueous solution because this is slightly soluble in water. And the acid is also soluble. H plus ion is also soluble. There's no state for the electron. So this is the oxidation half equation. As you can see, we have electrons transferred out, which is consistent with the definition of oxidation. So then let's look at oxidation of secondary alcohols. So for secondary alcohol, we have something like this. And when we want to oxidize this, we use the same condition, so H plus and Cr2O7 2 minus ion. And what will happen is we lose 2 hydrogens to form a double bond with oxygen. So in the end, we get ketone. So this is propan 1. So this is the naming of this compound. The last reaction with regard to alcohol is oxidation of tertiary alcohol. And because we know for tertiary alcohol, the carbon is connected to 3 other carbons. So there's no carbon to hydrogen bond for the central carbon connected to the OH hydroxyl group. So there's no reaction. So you cannot oxidize tertiary alcohol. It is resistant to oxidation. So how do you know whether the oxidation of alcohol have taken place or not? We can know this through color change. So we are using the dichromate ion as the oxidizing agent. And ultimately, the dichromate ion is reduced to Cr3 plus ion. And those 2 ions have different color. So the dichromate ion looks orange in color. And the Cr3 plus has a green color. So whenever you see your solution turning from orange to green, you know that your alcohol have been oxidized. Because both the alcohol and the carboxylic acid does not have any color. It is colorless. But you can tell the reaction from the color of the ions, the dichromate ion or the Cr3 plus ion in your solution. Now let's look at condensation reaction. So the condensation reaction commonly occurs with carboxylic acid. So it involves a combination. So you combine 2 molecules. and eliminate one small molecule. So this is typically just water molecule. So the product is the condensed form of the two reactions. So it's kind of joining the two molecules together. And one of the byproducts is a small molecule that has been eliminated. So a common example is the reaction between carboxylic acid and alcohol. So this is an example of condensation reaction. Because it forms ester, it is often called esterification reaction. But in the exam, you can also call it a condensation reaction. Doesn't matter. So what happens during this reaction is that the OH part from the carboxylic acid combines with the H from the alcohol to produce water. And then we establish a direct link between the carbon that is from the carboxylic acid and the oxygen that used to belong to the hydroxyl group. So this is the essence of our condensation reaction. And the product is ester because of this ester link, or the COO group. So for this reaction between carboxylic acid and alcohol, we require concentrated sulfuric acid as the catalyst. So let's look at one more example. So this is ethanol. We combine with ethanoic acid on the condition of concentrated sulfuric acid. The OH part from the acid and the H from the hydroxyl group combines to form water. And then we establish a direct link between the oxygen from the hydroxyl group with the carbon from the acid. And we get this ester linkage, or the COO functional group. Since we have two carbons on the alcohol side and two carbons on the acid side, it is named as isoethanoate. So we can also write this in semi-structural formulas. So suppose we have methanol and ethanoic acid undergo this condensation or esterification reaction. We would have CH3OH, which is the methanol, combining with ethanoic acid with CH3COOH on the concentrated sulfuric acid to form CH3. Remember, the H of the hydroxyl group would lose, and then we also lose the OH from the acid. We get CH3 COOCH3. So this part is the acid part, this part is the alcohol part. And as soon as we see the COO part, we know it's an ester. It is also soluble in water, plus one of the byproduct, which is water. The last type of reaction we are going to look at is the reaction between carboxylic acid and ammonia. So this is also an example of condensation reaction. So again, the carboxylic acid loses the OH, and the ammonia also loses one of the hydrogen to form water. And then we can establish a direct link from carbon to the nitrogen. So in the end, we get amide. As you would recall, this CONH2 is the functional group for amide. And the byproduct is also water, so it is a condensation reaction. For the reaction between carboxylic acid and amine, you get something even more interesting. So if we have acetonic acid and suppose we have methylamine, it is NCH3 NH2. We have something like this. The OH part and the H part would form water. And then there's a direct link between carbon and nitrogen. So we get CH3CO NH CH3. So this still looks like amide. But in this case, the nitrogen atom is connected to only one hydrogen atom. So it is actually a secondary amide. This is, by the way, not covered in the study design. So it's just some extension for those of you who are interested. So that's how you produce secondary amide. The last type of reaction we are going to talk about is hydrolysis reaction. So condensation reaction is the elimination of water. Hydrolysis is the addition of water. So this is used to convert back from ester to carboxylic acid and alcohol. So essentially we are reversing the condensation reaction. So the catalyst used in this reaction is dilute acid and heat. Remember, for the condensation we are using concentrated acid, but for the hydrolysis we are using dilute acid. For example, how do you name this firstly? So this should be called isopropanoate, because the alcohol part only have 2 carbons. The acid part has 3 carbons. And in this reaction, we want to add H2O. And under the condition of acid and heat, we are going to reform the acid by taking the OH from the water. So this is exactly what the acid has lost during the condensation reaction. And now we want to revert back this process. And similarly for the alcohol, we are gaining one of the hydrogen atom from water. So this is how we reform carboxylic acid and alcohol through this hydrolysis reaction. So now let's do a practice with regard to reaction pathway. So this is taken directly from the 2019 chemistry exam. So the first question is to draw the skeletal formula for pent2-ene. So let's have a go of this question. For pent, we need 5 carbon. So if I draw this M-shaped thing. You can see we have 5 carbon present. So this is how you draw the skeletal formula. So everything at the end represents a carbon, and every kink represents a carbon. And we want 2 E and E, so we want a double bond at the second carbon. So we draw it like this. So this is the skeletal formula for pent 2 E and E. And whenever you are doing this, I recommend you just to draw out the full molecule as well, to help you to understand what is going on better. So here we are using water and acid as one of the catalysts. So let's have a think of what reaction we are doing. So whenever you see water present, you know it should be addition reaction. It is not hydrolysis because you do not have an ester. You have something with double bond, and something with double bond is capable of undergoing addition reaction. And let's go back and check whether the catalyst for this reaction is H plus or not. So here we can see that the catalyst is sulfuric acid. So the catalyst is indeed an acid. You can also use H plus instead of H2SO4, because in reality it is the acid or the H plus part that is used as a catalyst. The SO4 2- ion is just a spectator ion, does not do anything useful. Okay, so we know it is an addition reaction. And here you are producing 2 compounds. And this is entirely possible because we can add the OH on the first carbon or on the second carbon. Maybe let's draw them out one by one. So if I add the OH on the first carbon, I get a primary alcohol. And if I add the OH on the second carbon, it is a secondary alcohol. So which one is compound N, which one is compound M? To answer this question, you need to know the definition of chiral carbon. So I have already discussed this in the previous video. I think it's the first video with regard to the organic chemistry. Chiral carbon means you have 4 different things connected to your carbon. So here you can already see that this carbon is connected to 2 hydrogens. So it is not a chiral carbon. But for this molecule, the second molecule, hydrogen, it is connected to hydrogen, OH, CH3, and a very long carbon chain. So indeed, you are connected to 4 different things. So you put an asterisk on this carbon, so it contains a chiral carbon. So the name of this is pentane. So you drop the E and indicate the position, which is on the second carbon, OL. So this is the name for this compound M. And now you are using the dichromate ion under acidic condition. So this is the catalyst required for the oxidation of alcohol. So you are oxidizing this secondary alcohol. And we already discussed in the video that when we oxidizing a secondary alcohol, we get ketone. So the semi-structural formula is just CH3, CH2. So we name from this side. Or doesn't matter, you can name from either side. CH2, CO, CH3. So this is the semi-structural form. So that's the kind of reaction pathway question you are expected to answer in the exam. So now coming back to the last topic I want to discuss is yield. So yield is a measurement of efficiency of your chemical reaction. So we always use the percentage yield, which is defined as the actual yield divided by the theoretical. So this is what you get, this is what you expect, times 100. So there are several factors that can affect yield. One is that you reaches equilibrium rather than completion. So this is heavily discussed in the previous videos with regard to chemical equilibrium. The second reason is the slow reaction rate. Maybe this reaction takes 3 years. So you need to be very patient if we want to obtain a very high yield. And also, maybe you are losing some of the product. If your system is leaking, or you are not careful in transportation, so things like that. So this is human-made errors, essentially. So let's have a look of this question. So you have 80 grams of propan 1-O. So we have 80 grams of propan 1-O initially. And in the end, we produced 55 grams of acid. So we want to calculate the percentage yield. So first, we know that the alcohol oxidized to acid in a 1-to-1 ratio. So 1 mole of alcohol will be oxidized to 1 mole of acid. So this is really important. So the mole ratio is 1-to-1. So first, we want to know the theoretical yield. So to answer this, we need the molar mass of the alcohol. So we have 80 grams of alcohol, and the molar mass is 12 times 3 plus 8 plus 16. So theoretically, you have 1.33 mole of alcohol present, and so you should also get 1.33 mole of acid. So this is in theory. So 1.33 mole of acid, if you times the molar mass of acid, which is 74, you should get 98.67 grams. And now you only have 55 grams. So using the formula actual yield divided by theoretical yield, 55 divided by 98.67 is 55.7%. So this is the yield of your chemical reaction. So another related topic is called the atom economy. So this is how effective we are using our atom in our reaction. So the percentage of atom economy is equal to the mass of atoms in the product divided by the mass of atoms in the reactant. So essentially, it's how well we are utilizing the atoms we have in the reactant. So for the fermentation of glucose, we want to calculate the atom economy. The mass of atom in the desired product is 2 times 12 times 2 plus 5 plus 16 plus 1 divided by 12 times 6, 12 plus 6 times 16 times 100 is 51.1%. So this is it for this video. In the next video, we are going to move on to a different topic, which is called spectroscopy. So how do we identify what organic compound we have produced?